This video will focus on determining the polarity of individual bonds in molecules. So to understand how to determine polarity in the bonds in individual molecules, you need to understand what polar is. And if we think way back to when we did bonding, we talked about how sometimes compounds share electrons and sometimes they transfer. And in the case when they share electrons, we actually talked about that sometimes they are a polar covalent share and sometimes they're a non-polar covalent share. And the difference between them is simply how they share electrons. Okay, so in a situation where electrons aren't shared equally, that creates a polar scenario, so an unequal share. So here's a good image of kind of the electron cloud of what it means to have the three different bond types: ionic, polar covalent, and non-polar covalent. And the blue here represents the electrons within the two atoms that are bonding. Okay, so A up there is a non-polar. You share your electrons completely equally, and they're distributed evenly across the two atoms, which are kind of like those two blue or black dots. B, on the other hand, is a polar covalent. They're still sharing, they're still overlapping like their electrons, but you can see that one side tends to have more electrons around it than the other side. So it's an unequal share, which leads to a polar molecule, it's called. And then C down there is what ionic looks like. You pull so strongly that you actually remove an electron away from something else, and now you no longer have overlapping electrons. You have complete separation, right? One positive and one negative. What you can see right here is the consequence of why it's important to talk about polar versus nonpolar. And that's that as soon as we have an unequal distribution of electrons, we have charge. And charge is what makes everything happen, right? Charge is what causes the electrons to stay near the protons. Charge is what causes chemical reactions to happen in the first place. It's the electron motion and the attraction that makes stuff happen. IMF is all about charge, right? So in a nonpolar situation, all the electrons are distributed evenly across the whole atom. Essentially, you have the same, if you think about like a simple atom coming together, let's say maybe fluorine, it comes up with the same number of protons and electrons, with another fluorine, same number of protons and electrons. In the end, all the protons in the nucleus, the electrons are distributed equally. There's no charge. All the pluses and minuses cancel. Now, in a scenario where one of the atoms might have the electrons around it more often, your positives and negatives add up to, again, cancel, but because there's a reason why they're on one side and not the other, we have this pooling of electrons, I always say, this area where more electrons reside than the other, and you can see it in this diagram, and that leads to charge. Okay, it's called a partial charge. It's not a full charge, but it leads to charge, and that's why polar is so important. If you have a polar molecule, you have areas of charge, and charge is interaction, and now it totally behaves differently. So how do you know whether the electrons are going to be shared equally or shared unequally or transferred? Well, we've talked about like metal bonding with non-metal versus non-metal bonding with non-metal as kind of our differentiation between sharing and transfer. But in the end, it's really more of a scale, we say. It's like a general idea of it depends on when two atoms come together, how strongly they're interacting, right? So if one atom is pulling the electrons really strongly away from the other one, they might fully ionic. But if one atom is pulling strongly but not enough to like rip the electron away, they might polar covalent. And if they're kind of like, meh, I'll share with you, like, yeah, we're good, then that would be like a non-polar covalent. And if you hear what I'm saying, the attraction of the electrons, be able to pull those electrons away, that's the electronegativity. So what I have up here is a general electronegativity table. Your table is a little different, but it's usually with these values we determine what type of bond it is. So if there's a really big difference in electronegativity between the two atoms that are bonding, then it's going to end up being ionic, which is why it's metal with non-metal. They're very far apart, so really different electronegativities. If they're a little bit of ways apart, but not enough to like rip them away from one another, that's polar covalent. So a decent difference in electronegativity, but not super huge. And if there's basically no difference in electronegativity or really small, then it's non-polar covalent. So to give you specific numbers, here is our guidelines. Okay, so polar means that there are charges. They're called partial charges, and you can see that symbol right there. That's a lowercase delta. I'll draw it on the board to help you, but it's kind of like sort of looks like a fancy S when I draw it. And those aren't full point charges, right? Ionic makes full point charges, positives and negatives. For polar, all of our protons and electrons are still canceling, but because the electrons are pooling on one side, I get a partial charge. Okay, and it comes on depending on how strongly the two things are attracting differently from one another. So nonpolar covalent electrons are shared equally, and the difference in electronegativity that leads to an equal share is essentially below 0.4. So 0.3, 0.2, 0.1, those are considered nonpolar covalent bonds, okay? A little bit of difference still is considered nonpolar. And then if you're equal to 0.4, all the way up to around 1.9, then you're considered polar. So unequal distribution, you have a great enough difference that's leading to these polar charges, and so then you have polarity. Over or 2.0 or over then ends up being ionic, great enough difference to lead to full transfer. And what we're going to find is not every metal-nonmetal combination leads to a 2.0, so that's a little like, oh, what about everything we've learned? The one thing about this scale, and you can see that big yellow arrow on it, is really bond polarity and bond charge. It's all about, it's a scale, essentially. It's not a hard and fast line. We give these hard and fast rules: 0.3 and below, nonpolar; 0.4 to 1.9, polar; 2.0 and above, ionic. But in truth, if you were in a lab scenario, we would use the properties of the compound to determine the type of bond. So there might be a case where all of a sudden something that's like 1.7 is exhibiting as ionic, and that's fine. So sometimes we think about this difference in electronegativity more as increasing ionic as I go more different, right? So totally equal, and then unequal, 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 eventually full separation. So I'm increasing how ionic my compound is. So the answer to the question, like how different is the electronegativity and what type of bond it is, you would use your electronegativity table. So it's absolute value, so the difference between your two numbers is your electronegativity difference. And then you would just say, is it 0.3 or less, nonpolar, 0.4 to 2.0, polar, or sorry, 0.4 to 1.9, polar, 2.0 and above, ionic, okay? And then you can compare and contrast them. The bigger the electronegativity difference, the more polar it is. So again, polar is just an unequal distribution of electrons that leads to partial charge, and charge is what makes the world go round, which is why it's so important. And we can figure out whether it's nonpolar or polar or even ionic based on the electronegativity difference. That's it. Have a nice night.